Hello and welcome to today's session. So today we are going to discuss on the new module that is on operational amplifiers. So operational amplifiers are nothing but it will basically amplify the difference of the two input signals and we will get it at the output. So it has various applications when we talk about an operational amplifiers. It can be used for a lot of mathematical operations like addition, subtraction, integration, differentiation and so on. So these kind of circuits, for example, if we have two different signals, or if we have two signals, if you want to combine it, if you want to add it, then we will use these Opamp circuits to add it. Or if you want to take the difference of the two signals, then we'll use the Opamp subtractor circuits. Likewise, we can perform integration, differentiation, lot of operations. Along with this, we can also perform the amplifier operations using these Opamps. We can also do the oscillators. We can make it design like oscillators, regulators and comparators. So based on comparison of two signals, we can generate a binary output either as 1 or 0 or something like that. We can do it. So previously these operational amplifiers were designed using vacuum tubes, where we all know that the vacuum tubes are quite big and large and it requires a very high voltage to operate. So nowadays these op-amps are reduced to such a smaller level. Now it is available in integrated circuits in a small ICs which operates at very less voltage. So this is about the introduction of this video. Now we will see the basic symbolic representation of this op-amp or operational amplifier. So let me write the symbolic representation of this op-amp. So it looks like this. So an op-amp has the two inputs and one output, and we used to connect an op-amp with two reference voltages. So this input, the first input we call it as V1 and the second input we call it as V2. So the first input is inverting terminal and the second input is a non-inverting terminal, and the output we call it as V out. And this reference voltage, this is positive reference voltage, this is negative reference voltage. So this is plus VCC and this might be minus VCC. So here this VCC voltage decides what should be the maximum output voltage that we are supposed to get from this op-amp. Now let me write here this as inverting terminal and this is my non-inverting terminal. Okay, so we have inverting and non-inverting terminal, and ultimately this total input we call it as Vin. So the input voltage we call it as Vin. So what is this Vin? So Vin is nothing but the difference between the two input voltages. So that is represented as Vin is equal to V2 minus V1. Okay, and ideally this op-amp has infinite gain. So it means by taking this difference of two input voltages, so that difference value is amplified to an infinite level, and that we will get it at the output. So that is a ideal case, but practically that is not true. So practically it is restricted to saturation level that is decided by this reference voltages. Now let us see the equivalent circuits of this op-amp. So if we see the equivalent circuit of op-amp, so we can see that ideally the input impedance of this op-amp is infinity and the output impedance is 0 ideally, and it has a voltage gain of infinity. So voltage gain we call it here, it has an open loop voltage gain, because the difference of these two input voltages, if it is amplified straight away, so then that amplification level or amplification factor we call it as a open loop voltage gain. And if you see here, that is V in is multiplied with AV, so then we will get as output voltage of that factor, that is the multiplied or the amplified factor. Now let us look at from this diagram. So now we're talking about the ideal case. So the equation is given by V0 is equal to AV into Vn. So this is nothing but it is AV of V2 minus V1. Okay. So let us come to the practical case, practical equivalent circuit. So if you look into the practical equivalent circuit, the input impedance is very high. So it might be in terms of mega ohms, hundreds of mega ohms also, and input impedance is very low. It cannot be zero, but it will be having an internal impedance of say a very less value, maybe 10 ohms or something like that. So then the gain is also infinity ideally, but practically it is restricted to certain values. So now let us come back to our equation. So let me clear this and let us take an example. So I had written the equation, an output equation, that is V out is nothing but it is AV of V2 minus V1. So in this case, let us take the open loop voltage gain. Practically, let us take this as 1000. There is no unit for this gain. So let me write this, a symbolic representation of this. Yeah. So this is our V1 terminal and this is our V2 terminal. This is inverting, this is non-inverting. We will come to this what is inverting and non-inverting later. This is V0. Now for example, I am going to apply a DC voltage here. So consider that I am applying a 4 volts at V1 and I am applying a 4.2 volts at V2. Now with respect to equation, so what will happen here? So we have an AV, so it is 4.2 minus 4 volts. So I'll get a difference of 0.2 volts and that is multiplied with 1000. So when you multiply this 0.2 with 1000, so we will get an output voltage of 200 volts, ideal case. But practically we do not get the output voltage of 200 volts. We will get an output voltage based on this, what is the reference voltage that we have connected here, that is V reference at this point. Now if we consider the maximum V reference that we have connected here is say plus 15 volts and here negative voltage is minus 15 volts, then we will get a maximum output voltage of that. So that we can see from this graph. Let me come to this, let me discuss this transfer characteristic graph of Opamp. Now here the x-axis represents the Vin and y-axis represents the V0. So now this slope represents the amplified output voltage. So if the difference of Vin, whatever it is, a point value, and if it is multiplied open loop gain, so we'll get corresponding value. Then what is the maximum output we can get? What is the maximum plus V saturation or minus V saturation that we will get is approximately equal to whatever the reference voltage we will get. So we will get only maximum that. So if I come back to our example, so ideally I am supposed to get 200 volts, but practically I do not get here 200 volts. I may get approximately equal to plus 15 volts approximately. Why? Because again this output voltage is not straight away decided by this reference voltage. It is depends on the load resistance which is connected across this. If the higher is the load resistance, then the output voltage will be closer to this reference voltage. So likewise, if we interchange this, now let us interchange this terms. Now if I consider this, V1 is 4.2 volts and this is 4 volts, then what happens to my equation here? The output voltage here is, it is 1000 of, now this is my 4 minus, this is 4.2 2 volts. So now it is 1000 into minus 0.2 volts. Now what is this minus represents? Because here the voltage at the inverting terminal is maximum when compared to non-inverting terminal. Maximum in the sense it is more. So with respect to non-inverting terminal, so the output voltage is an inverted of the input voltage. Now if you multiply, so I'll get a minus 200 volts. So this negative voltage is nothing but it represents the output is out of phase with the input. So that is the meaning of it. So that I will explain when I come to this differential amplifier modes. So hope you have understood with this example. So these are the ideal calculations, but practically the output is restricted to. Now in this second case, we will get an approximate output voltage of minus 15 volts. Okay. So now you have seen this transfer characteristic graph. So it represents after that whatever the difference voltage is multiplied with the open loop gain. So it will get saturated to this maximum reference voltages. So that is what this transfer characteristic graph represents. Now let us come to the block diagram of this Opamp. So basically it has three internal blocks, that is differential amplifier, voltage amplifier, gain stage, and push-pull amplifier output stage. So differential amplifier, basically it amplifies the difference of two input voltages to certain level. So it is the first stage of amplifier, and the second stage is the voltage amplifier, which will further amplify that signal, so that may use the class A amplifier. And push-pull is an final output amplifier circuit where it amplifies using the class B amplifier. So now there are two types of modes exist in an op-amps. So that is a differential mode and common mode. So now let us see what is this differential modes and common modes. So now we can see from this diagram. So in this diagram, we have not applied the input voltage to both the inputs. We have applied the input either to the inverting terminal or to the non-inverting terminal. So let me come back to this graph, and now let us write our op-amp circuit here. So now let us consider the single-ended differential mode. So in this case I am connecting my input to an inverting terminal, and the non-inverting terminal I'll make it as ground. I'll connect to ground point. So this is my non-inverting terminal, this is inverting terminal, and this is my output. Now here, what is my V2? Since it is connected to ground, my V2 is equal to 0, and V1 I am applying this voltage, so I'll get certain voltage. Now this is a sinusoidal waveform, so a sinusoidal wave appear across the output. So let us consider some input voltage, that is a sinusoidal waveform is connected here. Now what do I get at the output? Now since the input is connected across the non-inverting terminal, and output will look like this. So here, as per our equation, so this is equal to minus AV into V1. Why? Because our V2 is 0, so V2 minus V1, so V2 is 0, so we'll get minus AV into V1. So in minus AV into V1, it means here the input voltage is amplified with respect to AV, the gain factor, the open loop gain, and it is inverted by 180 degree. It means it is phase shifted by 180 degree. That is what this minus symbol represents. Now let us see the other case. Let me delete this. So if I take the other case, so rather than connecting the input to inverting terminal, if I connect the input to non-inverting terminal, let me connect a sinusoidal waveform to a non-inverting case. non-inverting input, then now we have V2 whereas V1 is equal to 0. So now the input waveform might be something like this. Then how does the output waveform looks like? The output waveform looks similar to the input, only difference is that the magnitudes are amplified because the V0 is equal to AV into V2 because V1 is equal to 0. Now if you see, if we connect an input to a non-inverting terminal, the output will be similar to the input in phase. It means there is no phase shift, it is in phase with the input. Only thing is that it gets amplified with the open loop gain. So now let us consider the ideal case. We know that from our equation, that is V0 is equal to AV of V2 minus V1. Now if we rearrange this equation, therefore it is V2 minus V1 is equal to V0 by AV. So we all know that ideally the open loop gain is equal to infinity and this is equal to 0. So then we can say that V1 is equal to V2. So what does it mean? So it means that the inverting and non-inverting terminals are at same potential with respect to ground. So this is what it means. So let me write it here. So it means that the inverting and non-inverting terminals are at same potential with respect to ground. So this is what this ideal case represents. So when in the ideal case, when AV is equal to infinity, so then V0 by infinity is equal to 0, then we will say that V1 is equal to V2. Okay. So now let us come to a double-ended differential mode. I'll just select this all and I'll clear it. So let us talk about the double-ended differential mode. So from this diagram you can see that in the first case is the double-ended differential mode. So here across the two inputs we have connected out of phase signals, the two out of phase signals here. So then what happens when we connect two out of phase signals? Ultimately it will get added up, both the signals are added up and it is multiplied with the open loop gain and the output is somewhat, it is the amplified added signal we will get. So how is that? We will see. Let us write the circuit here. So we have two sinusoidal signals here at V1 and at V2 it is another sinusoidal signal which is 180 degree out of phase. So now another end is grounded here. Now this is V2, now this is minus and this is plus. Now what happens like this? For example, it is phase shift of 0 degree and this is a phase shift of 180 degree. If I combine this, then what will happen? So then this input signal is, due to it is minus, so it will get inverted by 180 degree and that will get added up with this signal. So finally we will get an added signal of both with amplified with open loop gain. So we will get an output signal like this. So this is called as a double-ended differential mode. So this can also be written with just one symbolic representation at the input of an Opamp. So like this also we can write this notation. So what does this mean? So it means this is input with 0 degree phase shift and this with the 180 degree phase shift. It means we are applying a single input to both with 180 degree phase shift. So now let us look into the common mode. So what happens in the common mode? If you see from this diagram, in a common mode operation, so when we apply both the inputs with the same phase, same frequency and same amplitude, then due to the equation that is V0 is equal to AV of V2 minus V1, since both are of same phase and magnitude, what will happen? It will get cancelled. It will get cancel up. Whereas in the differential, in the double-ended differential mode, what happens is, so it is inverted and it gets added. So let us see this. Okay, so let me delete this and I'll write the double-ended mode, sorry, common mode. So here the inputs are applied with the same phase, if you can see here. So then what will happen here? So now, for example, both the inputs are in phase, same frequency, same amplitude and in phase. So when the amplitudes are same, when the frequency is same and phase is same, the output V0 is equal to 0, because it is very simple case, that is the input V in is nothing but that is V2 minus V1. When both the signals are equal and same, when you subtract it, both the signals, so basically it is minus of this, so it will get inverted. So what you get here is actually this. Then when it's get the inverting terminal get inverted, the input is get inverted by 180 degree, and when you add it, so what happens, the magnitudes get cancelled, so ultimately we'll get it as 0. So this action is also called as a common mode rejection. So let me write here, so this action is also called as common mode rejection. So this is very useful when we talk about noise when it comes to picture. Now for example, both these sources has a common noise, so if you want to cancel that noise, then in such applications the unwanted noise is there, so then we will apply this kind of circuit, then we'll get an output voltage of 0 volts. It will tend to cancel the unwanted noise. So that is the meaning of it. So okay, thank you for watching this introductory video on operational amplifiers. So in the next video we will going to talk about the parameters of Opamp, the ideal characteristics of Opamp. So thank you for watching this video. Take care.